All right, good morning. As you might have noticed that the quiz number 22 was out, which is about the topics we covered last Monday, which on the 17th and last week, I believe the 12th. Okay, it was mentioned in the quiz, at a different places that it's very very important for you to go through the graphs and go through the points, and which we did that in class, but it's also very important for you to have done that, to do that yourself. Okay, if you haven't done so, I highly encourage you guys to do those, and those are the foundation. Those are the foundation. Those are the basics. If you do that, a lot of those issues will be solved, will be trivial to you. If you don't, and there'll be a lot of other issues that you don't want to face, and it will bewilder and confused. So it's very important for you guys to go through those steps, right? The lessons we did on the 12th and the lessons we did on the 17th, and these are about these three functions and their inverse functions. Okay, and their inverse functions. So now, regarding how to find inverse functions, because we're gonna approach to alpha 57. Okay, alpha 57. Give the inverse function and graph those functions, right? And graph those functions. So now we're gonna approach that idea. Okay, we're gonna study that idea about inverse function. Then we notice that for inverse function, right? We did these pictures. We did these pictures last time, right? And let's see if you still remember how to mark these pictures. Yeah. You have a quiz on this, right? You have a quiz on these and a few other pictures. So the red, okay, the red is ln x, right? And the purple, what is the purple? Log base 2, right? Log base 2. The green is log base 3, right? And so this is e to the power x. Okay, so let's do the marking. Okay, so this hopefully will will help us to recall all those work we have done, right? Point by point, and their relative positions, They have a lot of the sameness in terms of domain and range, but they also have some subtle differences because they're not exactly the same function after all. So let's recap, right? So the black one here this is e to the power x. Okay, if you allow me, so let me use red, use black, so we can do some color coordination. Right, the black one is e to the power x. Okay, e to the power x. The purple here, the purple is 2 to the power x. Right, the green is 3 to the power x. And if we also like to be reminded that 3 is larger than e is larger than 2, and that picture seemed to be rather obvious, right? E is between 2 and 3. E is between 2 and 3. So when we take its power on this side, okay, we're talking about on this side, and the green is more narrow than the black. The black is more narrow than the purple. But let's look at the other side. Let's look at the other side. Okay, let's look at the other side. Did you guys write it down? The other side is seeing the relationship is reversed, right? The relative position is reversed. So did you guys write this down? Okay. If you look at the other side, right, the black is still in between. Okay, the black is still in between. I'm going to make it, I'm going to want you to make you see better of these. Okay, so let me do this. Let me clean this up. Okay, so what I'm going to do is I'm going to change the scale just a little bit. So we can see a clear, so make this 8 and make this 8. You see on this side, the relative positions seem to be reversed, right? You see on this one, how do we know which one is higher, which one is lower in terms of function values, right? How do we assess that? How do we assess that? So here I will give you some guideline. I will give you some guideline. On this side, the black and the green are separated. They're not together, right? That's why we can see them, right? If they overlap, it will be completely the black, right? Because the black absorbs all colors. Now, the purple, okay, so let's look and see which one is higher, which one is lower in terms of input output. Suppose I chose an arbitrary input. Okay, so I choose an arbitrary input. We shouldn't use the blue. I shouldn't be using the green. Let me choose a different color. Okay, I'm going to choose a color. Blue, right? Let's choose the blue color. And I draw a vertical line. I draw a vertical line. And I draw another vertical line, right? Okay, so the second vertical line I think is better. Okay, this is a vertical line. This vertical line, from this vertical line, okay, this signifies for that input, okay, that dot on the x-axis, okay, I deliberately make it, you know, not equals to the number we know. So you have to look at the heights, right? You have to look at the height. So we have 3 heights. We have 3 heights, okay? One of the heights is from the 2 to the power x, okay? 2 to the power x. So let me mark them again, okay? This is 2 to the power x. Okay, and the next one is e to the power x. Okay, on the green, it's a 3 to the power x. Is that clear? Okay, when I draw this vertical line, okay, when I draw this vertical line, so for that input x, okay, which is that's where the heart is, okay, for that input, we will have 3 output, okay, we'll have 3 output. The first output will be the purple, of course. Okay, the purple. I can use the straight line. Purple. Okay, the purple is the value you get. It's a function value you get for 2 to the power x. And the black, I'm going to use the black for e to the power x. Okay, e to the power x. So I'm going to measure, but I'm going to also want you to see the purple, right? That's how high it is. So the black is higher than the purple. You guys see that? That means e to the power x is larger than 2 to the power x. Okay, because it's higher. They're all positive. They're all positive. Okay. The green is measured from here. You can see the green is even higher. You guys see that? Okay. So when we talk about more narrow, more and wider, but that doesn't, that just tell you the how, how far they are apart from the y-axis. But in terms of function value, when x is positive, you can see when x is positive. Okay, so I want you to look at this table. Okay, last column, more row. Okay. The software sometimes just properties. Let's see if I can move it up. It doesn't move up for me. Okay. So what do we see here when x is greater than 0? Okay, when x is greater than 0, what happens? You saw it. Okay, the green, which is 3 to the power x, is larger than e to the power x, and it's larger than 2 to the power x. You follow me? When x is larger than 0, okay, on this side, okay? Is that clear to you guys? Because I may have to adjust the picture. Okay, so let me do it again. Does everybody follow me? I draw a vertical line. Okay, with the color of blue, Okay, so I selected an input, and this input is going to be right here. So I'm going to just arbitrarily choose an input. So this input has a corresponding output. And so this is the vertical line. This vertical line crosses the purple, crosses the black, crosses the green. Okay, and each height is the value for 2 to the power x, e to the power x is 3 to the power x. Does that make sense? Okay, I will give you examples. Okay, I'll give you examples after this that we can calculate. Now, in this case, visually, I want you to see the visual. From the purple crossing, right? The purple crossing, that's the function value, which is a 2 to the power x. It's a purple, 2 to the power x. And this purple is shorter than the black, which is e to the power x. Do you follow me? E to the power x. Okay, so this is a little bit, I don't want it to be overlapping. Okay, then you wouldn't be able to see it. Okay, so the black, the crossing with the black is this much. Okay, so you can see both the purple and the black. You can see the black is higher. The black height is the value of e to the power x. Do you follow me? The purple height is 2 to the power x. And of course, you understand the green height, okay? The green height, which is measured from the crossing here, that's going to be higher than both of the other two. Okay, so that tells us that when x is positive, 3 to the power x is larger than e to the power x is larger than 2 to the power x. Do you guys get that visual? Yes, you get it? So that's the visual. Okay, numerically. Okay, let's look at numerical value. Okay, numerically we can calculate, right? For example, so I'm going to give you an example here. Okay, examples. Okay. Example, I'm going to choose, say, let's start from something simple, right? When x equals to 1. when x equals to 1, 3 to the power of 1. Okay, 3 to the power of 1. This is 3 to the power of 1. 3 to the power of 1. 3 to the power of 1. So power of 1, we can omit the power. So 3 is larger than e, larger than 2. We know that's a fact. Okay, so what does that mean for the vertical line idea? Okay, for the vertical line idea. Okay, so let's do this again. If x equals to 1, I'm going to draw the vertical line, which I'm going to still make it blue. So x equals to 1 right here. I'm drawing the vertical line, right? And this vertical line, you can see it crosses the purple, crosses the black, crosses the green. Okay, and what are those values? What are those values? The purple height, okay, the purple height is equals to 2. This tells this height is 2. This height is 2. Okay, and the black height, what is the black height? The black height, okay, measure from the crossing. Okay, measure from the crossing with the black. Okay, and that is E. Okay, you also see the point 1 comma E, right? 1 comma E, that's the same thing. So this black is E. And the green, which is here, the crossing is here, they're so close together, right? Is E, and that color, I'm gonna make it green. You can see the crossing, okay? That's the crossing and the height, which is a green, and that is a 3. Do you guys follow me? So you see that visual? So indeed, E is between 2 and 3. And graphically, you can see the green is higher than the black. The black is higher than the purple. Do you follow me? Yes, everybody? Does everybody follow me? Any questions? I want you to see that visual. That's the visual. Okay, that's what the graph is for. Okay, graph is to help us observe, you know, input, output, and the relationship between input and between output. Okay, but this is for x is larger than 0. What if x is less than 0? You can see on the other side, the purple actually the highest. The purple is 2 to the power x. The black is still in between, and the green is beneath. You guys see that? For the same reason, Okay, for example, at this point, -1, at this point, -1, okay? You can see the relationship is reversed. The relationship algebraically, okay, so did you guys write this down? Did you guys write this down? Okay, once you write it down, I'm gonna clean this up. I'm gonna try to make these separated, okay, by making adjustment to the graph. Okay, so I'm gonna make this 5. Hopefully they can be apart, right? And the other piece I'm gonna make it apart is that this is maybe -1, -2 first. But you can see the green is below, right? The green is below the black, okay? The green is 3 to the power x, the purple is 2 to the power x, and the black is e to the power x. You guys see that? Okay. So for the input of a -1, right? We know on the black curve is 1 over e. That's the input. Input a -1 and the output is 1 over e. And obviously you can see the purple, right? So I'm still going to draw the blue line. Okay. for the input of -1, I'm going to draw a vertical line. This vertical line, as you see, for that input, okay, that input is a -1. Okay, if we plug in -1, right? If we plug in -1, okay, if x is negative, okay, I'm going to put in for x is negative, okay, and the example is I'm going to make another column. The example is I'm going to choose x equals to -1. How about that? Okay, so that I hopefully make it easier for you to see. Okay, so that vertical line is still there, thank God. Okay. For x equals to -1, you can see the value 1/e is the height of the black height. Okay, 1/e. How high is it? From the crossing, that's how high. Okay, that black height is 1/e. Okay, that's 1/e. I'm going to put it here, 1/e. Okay, and how about the green height? The green height, that's from 3 to the power x, is right here. You guys see that? It's a little bit shorter, right? It's a little bit shorter. Okay, so that's a green height is 1/3. Okay, 1/3. Okay, I'm going to separate them. They're not multiplication because we're going to compare their size, right? The next one, from the purple crossing, the crossing with the blue with the purple, and that will give us a height. I'm going to use a purple height. That purple height, of course, is from the crossing here, and that's going to be this much. You can see the purple is higher than the black. The black is higher than the green. And the purple, what is the purple? The purple is from 2 to the power x, right? This is 2 to the power x. This is 2 to the power x, right? The green is 3 to the power x, right? So at this point, when x equals to -1, what happens? The height, which is the purple, hold on. It messed me up, but that's half. That's half. Okay, I'll do it again if necessary. So obviously the purple height, which is half, is larger than the black, and the black is larger than 1/3. Do you guys follow me? Do you guys follow me? So that's the visual. Yes or no? Any questions? Okay, so these are, let me see if I can move it back. There, I move it back. Okay, you can see that when x is positive, 3 to the power x is larger than e to the power larger than 2 to the power x. If we move it to the other side, the relationship is reversed. Okay, so when x is negative, this relationship is what? It's no longer true. Okay, it's reversed. Isn't that interesting? Isn't that interesting? You follow me? Okay, so on this other piece, okay, do you guys get that? So depending on x is positive or x is negative, the function value, okay, in terms of their sizes, the value have differences. okay? E to the power x, of course, is always in between. It's always in between. But on the positive side, it's going to be between 3 to the power x higher, 2 to the power x is lower. And on the negative side, 3 to the power x is lower, 2 to the power x is higher. Got it? So let's look at the logarithm. Let's look at the log. Okay, let's look at the log. Log cases has a similar situation, isn't it? Okay, it has a similar situation. At input 0, they overlap. That's the common x-intercept. That's the common x-intercept, okay? So let's clean this up. Okay, these are the details we must observe because a lot of them in the future, some of your math is going to use these facts. It's going to use these facts, right? So this is a so-called a picture tell 1,000 words. A picture does tell 1,000 words, but we have to be able to find those 1,000 words, right? So now let's look at the logarithm piece. Logarithm piece, okay? On the logarithm piece, and you're going to see similar reversal. Okay, suppose I draw a blue curve here, vertical line, right? And versus I draw another blue straight line over here, right? This represents the input. This input is larger than 1. And this input is smaller than 1, between 0 and 1. Because we know logarithm, it doesn't, the domain must be greater than 0, right? So it's all positive, but 1 is larger than 1, 1 is smaller than 1. Now, you can see on this side, the purple is on top. And here, the purple in the bottom. The green is in the bottom. Now the green is on top. Do you guys see that? So that's the value in terms of sizes. That's in terms of sizes, okay? So you can see I can draw the purple height is larger than the red height. The red height, of course, is e to the ln x. So let's mark these, okay? The red is ln x. The purple, okay, what is the purple? The purple is log base 2x. Okay, log base 2. Oh, sorry. I mean to write in purple. The purple is log base 2x. And the green, and what is the green? The green is log base 3x. Okay, so between these two intervals, okay, the value size, the values are different. The values are different. Okay, the values are different. Do you guys see that? So I want you to observe that. So it's very similar to what we did before. The sizes are reversed. The sizes are reversed. So let's see how we express it, right? Let's see how we express it. I'm going to set up a table. I'm going to set up a table. Let's see where I'm going to set up the table, okay? So what I'm going to do is that I'm going to set up another table because I want you guys to get familiar with those expressions, okay? How we express it, right? We see this is higher than the other one. How do we express it mathematically? Clear, just clean it up, okay? I'm going to clean this up and let's focus on these 3 logarithm curves. Okay, let's look at these 3 logarithm curves. Put it down beneath. Okay. And wait. Okay. on this piece, on this piece. Now, we're going to draw a similar table. We're going to draw a similar table. 2 rows. 1, 2. One more column. Right, one more column. So this time our focus is this piece. Is this piece. Okay, I want you guys to mark it with me. Okay, mark it with me. Okay, so this is, I think this is good enough. Okay, all right. So ln x is a red. Okay, the purple is log base 2x. Okay, the green is log base 3x. These relative positions give us a lot of perspective, because if I ask you where is going to be common log 10, log x going to be? Is it going to be above all of these, or is it going to be beneath all of these? Right? Anybody want to take on that question? If I want to draw common log x, right? If I want to draw common log x, where do you think it's going to be? Is it going to be above all of them, or is it going to be below all of them? Base 10. This is base 2, base E, base 3. So where will be log 10? Is it going to be over here, that way, or is it going to be over there, like that? Do you understand my question? Do you understand my question? If I'm asking you to sketch log 10 on this picture, quickly, where do you think it's going to be? Can anybody give me some educated guess? Just a sketch. It doesn't have to be precise. We want to have the relative position correct. Excuse me. We want to have the relative position correct. Where is it going to be? Alan? Francisco? Marcelo? Could any one of you tell me? No penalty. No penalty. So how would you guess it? Are you gonna, you look at these three curves, you say, oh, you look, on x larger than one side, log base 2, x is higher. The base is smaller than e. And ln x is in the middle, and the base is 3 is the largest base, but it's not as high as the other two. So where do you think log 10 is going to be on this side? Is it going to be here, or is it going to be here? Tell me, is it going to be here? Oh, let me not use the green. Okay, let me not use the green. I'm going to use I'm going to use yellow. How about that? Right? Log x, is it going to be this guy, or is it going to be this guy? I'm just sketching. This my sketching is not very pretty. Is it going to be this one, or is it going to be this one? Yes or no? Which one? Okay, you're not answering that question. I guess you don't want to be embarrassed. How about you write down your answer on your paper? Bottom yellow. Bottom yellow. Okay, so bottom. Very good. Okay, I'm not saying yes or no yet. Okay, Alan. Okay, I think your guess is very close to the fact. Okay, you're right. You're right, because you look at the pattern, right? So now choose to be revealed. Choose to be revealed. Where would it be? Right? You can just use your comment. You just use a calculator, right? I'm going to choose a color, the color purple. How about that? I'm using purple again. No, I'm sorry. This is two purples. Okay, two purples. That's not right. I'm not using purple. I'm going to use, oh yes, this blue, light blue. Where does it show up? It show up right there. No, wait a minute. This software is not working properly because that's overlap with E. Do you have a calculator? I don't think this is right. Okay, this is not right. Why we think it's not right? Why we think the software is not doing right thing? Because we have reasons, right? It should be below all of three, right? It should be below all of the three. For example, if we plot a point, on log, on common log 10, right? We plot some points. Okay, let's just verify our point because at this point, this is ridiculous. Well, I shouldn't be so adamant about it. Okay, so log x. Let's use black. You see, it shows ln x. It shows ln x. That's not right. That's not right. Right? We know that's not right. So what do we need to do is that we have to sketch our own. We have to sketch our own. Right? How do we sketch our own? This is the curve we didn't do, right? So suppose I choose x equals to 1, right? Log 1 equals 0. That still crosses this point, 1 comma 0. Okay, x equals to 1. If x equals to 10, what will happen? Log 10 equals to 1, right? Where's log 10? Well, I need to extend this picture just a little bit more to up to 11, right? So log 10. So if I put the points in place, you can see you can totally control the situation, right? So 10 comma 1, and that's a dot, okay, a black dot, okay, and these two dots should connect, right? These two dots should connect. That's for common log 10, common log x, right? So if we connect these two dots, your conclusion is right. Even though the software gave us the wrong answer, because I didn't expect that. And you are educated to guess. It's perfect. Great job, you guys, right? So it should be beneath. It should be beneath. So this yellow is what? Should be log x. Well, obviously the software is not going to make it, right? And I think your calculator probably give you a better picture. Do you guys have a graphing calculator will give you that picture? Yeah? No? 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 Yes? You should see that. But if you don't see that, that's not a big deal. I have another software that I think might do the trick. So even if we have technology, we still have to think, is it right? Right? Maybe this software didn't implement common log x. I think that would be the better guess. Okay. So what I can do, actually, I can make this software to produce that picture. Okay. Let me just give me a little bit calculation time. Okay. So ln x, ln 10. Okay. So I'm gonna try to do this picture with the software, okay? Because I know what the software cannot do, but I really just don't want to spend too much time to so I should do ln x over ln 10 to see if that curve will draw. There. Okay, I use the change of base formula, which we haven't covered in class. Okay, so that confirmed this is a common log x. Yay! I'm proud of myself because I was thinking, if you don't have a log x, what we can do change of base formula, right? We will cover this later. We'll cover this later. Do you guys see that? So you guys' guesses are correct. Perfect. Right? You just have to plot a few points to make it happen. Okay. Oh, it's actually an interesting discovery. I've been using this software for a long time. Okay, for my, from time to time. Not when I was teaching on site, I don't use it as much. When I teach it online, I use it almost every day. But you can see the shortcomings of software. And just I see some of the shortcomings. So don't trust the picture yet until you verify a few things. Okay. Good lesson learned. So we got our log base x. So once again, okay, so let's mark these. Okay, we draw a blue line, right? Vertical line. Which one is higher? Can you mark these with me? This is what? This is log base 10. And the green, what is the green? Log base 3. And how about the red? The red is ln x. And what's the purple? What's the purple? Log base 2x. How about the other side? The other side is reversed, right? The other side is reversed. So let's draw another vertical line. Okay, we didn't do 10 to the power x. If we do the 10 to the power of x, right? I'm drawing another vertical line here. I want you to guess 10 to the power x. Where is it going to be? Is it going to be above all three, green, black, purple, or below all three? I want you to guess it. I want you to guess it. What'd you get? If I am to draw 10 to the power x in the same picture, 10 to the power x in the same picture, where do you think it's going to show up? I'm adding 10 to the power of x. What color I'm going to give it to? Let's see what color that we haven't used. This one, pink, light blue. Let's use light blue. It should draw this picture. Light blue, look at that, right? So light blue is the highest. Light blue is the highest. Okay, so if I draw another vertical line, right? There. So this is, so let's mark it with me. Okay, how about you guys mark it with me? The blue is 10 to the power x, right? The green is 3 to the power x. The green is 3 to the power x. The black is e to the power x. And the purple is what? Is 2 to the power x. Now compare. Compare. And on the other side, they're reversed. On the other side, they're reversed. You follow me? You guys follow me? This is how you observe these. This is also the reason I want you to do number 56. Okay, you not only do it, vertically, you also do it horizontally to do the comparison. And this thing we do is called a study. This is called a study. You study every aspect of it in comparison until everything is completely clear. What's the same, what's not the same. Okay. So far, so good? Are we good? Okay, now I learned something about the software I use it for so long, right? There's certain things it doesn't do. It doesn't do, but I can make it do it. I can make it do it. All right. And they're all inverse function to each other. They're all inverse function to each other. And last time we have summarized, right? We summarized. So let's go from the summary and we're going to talk about inverse function, which is what we initially set out to do. Okay, initially set out to do. Did you guys write it down? Did you guys write it down? Okay, I'm leaving these on the picture. I want you guys to write it down. Which one is higher? Which one is lower? Okay, so now we're gonna because we talk about input output, it's just larger, smaller, just these comparisons. So wider, narrower, and those are just visual and it's relative to certain things. But if you talk about higher, lower, it's more relevant because or larger, smaller, this will be more relevant. Because when we talk about input output, when input output are addressed. Are you done writing them down? Are you done writing them down? So this picture should be very revealing about all the functions we talk about, we address in Alpha 56 in terms of their relative relationship, right? So we have a relationship horizontally, right? Number 1 and number 2. We also have relationship from 1, 3, 5, 7, 2, 4, 6, 8. So these are the other layers of relationship. We want you to study. We want you to study. Are we good? Did you get it? And we also talk about that they're inverse to each other. They're inverse function to each other. For example, the purple, right? The purples are inverse to each other. Okay, and the black and the red, these are inverse to each other. E to the power x and ln x, they're inverse to each other. And the green, the green and green, they are inverse to each other. Okay, and the blue and the black, the blue and the black. Oops, I mean to have a different color. Okay, let's see what color I'm going to use. Let me use blue. Let's use the blue. Okay. It's hard to decide. Okay. The blue, which is 10 to the power x, and the common log x, they're inverse to each other. So you can see this table, if you study thoroughly, a lot of the questions will be no questions at all, no questions at all, very clear. Okay, so these are the visual. And these pairs of inverse function to each other, they have something in common. They share the same line of symmetry. And that same line of symmetry is y equals to x. Y equals to x. Okay, they share the same line of symmetry, right? As we saw in those details, right? You switch the input and output, you get the other one. You get the other one. So far, so good. And let's look at the algebraic expression. Let's look at the algebraic expression. Okay, are you ready? I'm going to clean this up. So you're not going to see this anymore after I clean up. Did you write them down? Okay, I assume you have done it. Okay, so that's what we have studied, and this time I'm going to make it color matched. Okay, because I have a little shortcoming. This is red. It should be ln x. Okay, this is red. It should be ln x. Come on, ln x, show up. Right, I'm going to make it black. So this way, it will match the e to the power x. They're inverse to each other, right? And this is a common log x. I'm going to change it to blue. Common log x. I'm going to change it to blue. There. Okay. So this time they're color matched. This time they're color matched, right? They're inverse function to each other. They're all symmetrical with respect to this y equals to x. And they have the same, these also 1, 2, 3, 4, they have the same domain. And these 1, 2, 3, 4, they have the same domain and they have the same range. They have the same range, okay? How about horizontal asymptote? All 1, 2, 3, 4, right? They have the same horizontal asymptote, which is y-axis, which is x equals 0. And all three, 1, 2, 3, 4, all four have the same vertical asymptote, which is the y-axis, x equals 0. Okay, so we studied those yesterday. And of course, there are other interesting properties to study as well. Okay, so how do we get inverse function? How do we get inverse function? Okay, that's what we're going to study because we're going to get to 57. We're going to get to 57. All right. Now they're color coordinated. They're color coordinated. So let's get to the inverse function. Okay. We have, so I'm going to expand this table. I'm going to expand this table. This table will be expanded to what? 10 to the power x also can join this table. And the next one is log x, can also join the table. And all of these still applies to those respective functions. Okay, all of those are similar. They're similar. Okay, so since 2 to the power x and log base 2x, they are inverse to each other. Let's see what we can derive. Okay, let's see what we can derive. Okay, to find inverse function. To find inverse function. Okay. I'm going to take a pause from the current topics. And we are going to address the finding inverse function. I want to see if you guys have learned this before, okay? If you guys have learned this before, okay? For example, suppose I give you a function, y equals to 2x minus 1, okay? If I tell you this function has an inverse function, okay, suppose I call this function f of x, okay, and this function has an inverse. Would you find it for me? Would you find it? Not for me, just for yourself. Would you find it? Have you learned this technique? Okay. To find the inverse function. Okay, so we're going to find the inverse function. The first step is to swap x and y. Swap x and y in this relationship. So in this equation, okay, we view it as an equation or if statement, we swap x and y. So x turn to y, y turn to x. And then solve for y. These are the general procedures to find inverse functions if the inverse function exists, right? So we're going to solve this equation and to isolate the y, Okay, so what do we do here? And then we're going to have 2y equals to x plus 1, right? You just add a 1 on both sides, 2y equals x plus 1. And next, we're going to divide both sides by 2. So y is equals to 1/2 times x plus 2. X plus 1, sorry, x plus 1. Have you learned this before, guys? Have you guys learned this before? If you haven't, and this is the first time you see it, that's okay too. Have you seen something like this being done before? Have you? No? Yes? Okay. No answer. Ellen, have you learned this before? No answer. Okay, but that's fine. That's fine. You guys are probably busy and you come back to watch the recording. But I really hope that if you are here, your participation is much appreciated. Anyway, without further ado, so we have talked about the general procedure to find inverse. Okay. But once we find the inverse, let's see. This is the function, right? Its inverse is this guy. So we're going to give it a name. So this is the inverse, right? And we're going to give it a name. We call it f of inverse x of x. So that's how we express function and its inverse. Okay, this is the function and that's the inverse. Now the question is, if a function has inverse, how many inverse does it have? And the next question is, right? The first question, if a function has an inverse, how many? The next question, does every function has an inverse? Okay, good. Yeah, I'm here. I'm learning as we go. I don't want to answer something wrong. Okay, it's okay. Thank you for your input. I understand. I know it's but if you answer, that's great. If you don't answer, then that's I know you guys are there. Okay. I know is a lot of us have you need more confidence, right, about what you do. But I encourage and I enjoy the interaction. But you answer question only when you feel comfortable. Okay, no problem at all. So we have two questions here. I have two questions here. if a function has an inverse, how many? Right? So for example, for this one, we have found an inverse. Now the question is this the only inverse, or do we have another one we haven't found? Right? Do we have another one that we haven't found? Well, the answer is, here's the answer. Okay. If a function has an inverse, it is unique. It is unique. It has, if you find one, that is the one, and there's no others. Okay, so this is the answer to the first question. The second question is, does every function has an inverse? The answer is no. The answer is no. Okay, some function has inverse, some function do not have inverse. Okay, so the answer is, then you say what kind of function for sure have inverse and what kind of function that do not have inverse, right? So the next question comes forward, right? Only the one-to-one function okay, only and a one-to-one, so I use a, we'll use n. Only a one-to-one function has an inverse. And of course, if it has inverse, it's unique. Then you see, what is a one-to-one function? What is a one-to-one function? I think we talked about this concept before, right? Did we talk about this concept before? Right? What is a one-to-one function? How do we identify a one-to-one function, right? So we're going to talk about what is one-to-one function. Right? What is a one-to-one function? How to identify one-to-one function? How to identify? Right. So we have. So please write them down. Okay. So we get to that. If a function has an inverse, it will be unique. Okay. Does every function has an inverse? The answer is no. Some function has inverse, some function don't have inverse. What kind of function has inverse? Only the one-to-one function has inverse. And the question is, what is a one-to-one function? Okay. The definition the definition of one-to-one function actually is on page number 2 of the notes. Okay, on page number 2 of the notes. So I'm gonna if you have the notes with you, so please, okay, so please identify, please find that page. Okay, I want you to write this down. Okay, so a one-to-one function is defined as follows. Okay, a function with domain A is called a one-to-one function if, okay, no two inputs, I'm going to modify my definition. Okay, so because those are, I copied from some textbook, but I think I'm going to modify and make it no two different input have the same outputs. Okay, so we're going to use the language we're more familiar with. okay? Which is comparable with the no two elements, the two element must be different, okay? No two different input have the same output. What does that mean? Okay, that is okay. The function, suppose I call the function f is the domain A, and it works on input 1. It also works on input 2. Input 2. Okay. Whenever input 1 is not the same as input 2, and their output are not the same either. So this has to be true for any two inputs. So whenever the inputs are different, their outputs are different. Okay, so that's the definition. That's what it means. No two different inputs have the same outputs. Okay, so how is that translated into picture? Right? How is that translated into the picture? For example, the situation of the line we just did. Where is it? Where is it? Where did I put it? Right here. Right? And we know this is a straight line. Right? We know this is a straight line. Right? Is this one-to-one function? The question is. I told you that it has the inverse. It is a one-to-one function. This is one-to-one function. And what does it mean that for different input, it must have different output? Okay, so what is the graphical meaning of it? Okay, so with all these definitions write down. So could you guys write these down for me, please? And we're going to go back to that function to observe what is the meaning, what is the picture, what is the meaning on the graph. Write this definition down. Write this definition down. It's actually about time we take a break. Okay. Did you write it down? Okay. Now, let's go back here. Oh, this has to be true. Sorry, has to be true for any any input x1, any input from x2 from the domain. Okay, from the domain A. Okay, so this has to be true for any two inputs, you name it. It has to be true for the entire domain. Okay, so now let's look at this situation. We're going to explain one-to-one. We're going to explain to one-to-one. Okay. I think I'd rather you guys take a break because we do have a lot of information here. And I will leave the one-to-one function concept over here, and we will come back to work on the one-to-one and how how it's being reflected on these pictures, okay? And then of course we're going to come back to talk about the logarithm and exponential functions we did. All right, so take a break for 10 minutes. Okay, so come back at 11:50. Okay, come back at 11:50. And so take a break. Okay, I'll continue from where we left off, right? We talk about the definition of inverse function. So next we're going to look at these functions. So how do we identify when input are different and output are different, and vice versa, right? Some of you guys might have learned something called vertical line test, horizontal line test. Do you guys remember those? Anybody have learned that? If you haven't, no big deal, right? The vertical line test refers to that it's a function. You draw a vertical line, it crosses the curve at one place, right? And this function we have here, right? We're going to draw this function. It's a straight line. We already know that, right? We already know that. So it's a straight line. Okay, so let me just move it closer to us. Okay, for different input and we have different output. That's the definition of one-to-one function. But first of all, is it a function? Of course, it's a function, right? What's the definition of function? We learned the definition of function before, right? For each input, there's a unique output. For each input, there's unique output, right? For example, in this case, right? For each input, right? Suppose I have an input. For each input, and there's a, so we draw a vertical line. We've done similar things before. Remember, we did similar things in a quadratic, right? And we draw a vertical line. And it will cross the curve at exactly one place. So that's this is the input. Okay, so let me draw the input. The input, I will make it, it doesn't matter what color. Okay, this is the input, the purple. And the output, make it red. So for each input, there's unique output. For each input, there's unique output. So that uniqueness, that one crossing, okay, that one point of crossing, and everywhere in the domain, that makes function. So this vertical line test is to test whether it is a function. For one-to-one function says that different input, we must have a different output. Okay. In other words, if you draw a horizontal line, if we draw a horizontal line, right? This is about output. How many input will correspond to it? There's one and only output, right? So given the output, right? This output is this much. Okay, it crosses the curve at exactly one point. And the respective input is this much. Sorry. The respective input is this much. Purple again. Okay, so to test if a function is one-to-one, you just have to draw these horizontal lines. Each horizontal line cross it once. So not only you have the vertical line test pass, you have this vertical line drawing is also pass. And what does it signify? What does it signify? Right? For different input, right? Let's go back to the definition. For different input, there's an input here, and there's another input here, right? The input are different, and their output are also different. Their output is also different. Okay, so the height are the output, and the input, of course, would be, and this is one input, and this is the other input. So for different input, there are different output. So to test if a function is one-to-one, all you have to do is you do, after you've done the vertical line test, you do the horizontal line test. That's to test if the function is one-to-one or not. If a function is one-to-one now, it is unique. The one-to-one function has a unique input. So this is the, let's summarize, right? Let's summarize this piece we talk about. Okay, so let's summarize this piece we talk about. Every one-to-one function has a unique inverse. Okay. And only one-to-one function has inverse. Then you say, well, we just talk about not every function has inverse because not every function is one-to-one, right? In comparison to another function we talked about before, the x squared function, right? It's a parabola. We have studied, parabola. This function certainly does not pass the horizontal line test. Okay, it doesn't pass the horizontal line test, right? If we draw a horizontal line, right? It crosses at two places. And therefore, it doesn't have inverse. It doesn't have inverse. Got it? All right, so let's continue these topics. Okay, wait. Clear all drawings there. So this is the example, a function without inverse. Okay, x squared is not one-to-one. We have addressed these issues before. Okay, it's not one-to-one. All right, so this function has inverse, and we actually found the inverse. So if I draw this inverse function along with the given function in the same picture, what do we see? Okay, I make it red. That's the inverse. If I adjust the scale, right? So this is a -5. I make it 5 here, -5, +5. I just make sure the scales are uniform, right? This much is 2, this much is 2. Guess what? These two lines, they are also symmetrical with respect to that green we have talked about before. You guys see that? Okay, these two are inverse function to each other. Okay, so this is a f, and this is the inverse. Okay, this is how you write inverse. When we put the function and its inverse together in one picture, and they are always symmetrical with respect to this green line, and this green line is y equals to x. And it is the same as this, with the other one. Okay, so please write it down for this example. Please write it down for this example. And then we're going to look at some other interesting features, right? Each function has domain and range, right? Each function has domain and range. And if we go back to look at the steps, we went through to find the inverse, there's one particular step that we swap x, y, and this is not a simple swap of the symbols. It's also a swap of domain and range. It's also a swap of domain and range. Okay, we're going to see more of this. For these two functions, their domain and range are the same. Okay, for example, so if you swap them, it's not going to make any difference, right? It's not going to make any difference. For example, in this case, f of x, right, is this function. Oh, wait, here, right? And its inverse is that guy. Okay, the domain for this guy is all real numbers, right? So from -infinity to +infinity. And the range is also the same, right? Remember we talked about these issues, right? With exponential logarithm. We're gonna go back there. So when we swap domain and range for the other functions, there's no difference. You just swap, right? You swap, they're the same. There, you don't swap, they're not the same. Are there situations they're not the same? Yes. And that's our exponential function and logarithm function. Okay, so now you see some commonalities, right? We see some commonalities. So now let's go back to these. Okay, to these table, we have worked so hard for more than a week, right? For more than a week. And I also gonna bring the curve with us, right? We drew them, we have worked them, we observed them. We've done so much work with them, right? Now, we know they're inverse function to each other. Okay, 2 to the power x with log base 2x and so on and so forth. Did you see the swap of domain and range? Do you see the swap of domain and range? Okay. And everything else the same. So that swap resulting the swap of domain and range. Larger than 0, larger than 0. Domain larger than 0, range larger than 0. Domain all real numbers, range all real numbers. Do you see that swap, right? That swap. This is because the swap. The swap. Okay. And then your next question may be, could I solve the same way as could I find the inverse the same way as I did with that lines? Yes. Yes, I'm going to show you that part as well. Okay. For example. Okay, now, before we do that, okay, because these two are inverse function to each other, so I'm going to write F inverse now. Okay, I'm going to write that as well. Okay, they're corresponding to each other, so we don't need more to explain. Okay, so can we use the same procedure? Okay, can we use the same procedure as we did here to find inverse for our logarithm? The answer is yes, absolutely. Absolutely. The only difference is the functions are different. We're going to follow exactly the same track. Okay, for example, 2 to the power x. Okay, does this function has the inverse? Right? Does this function has 2 inverse? So 2 to the power x. Does 2 to the power x have inverse? Well, we have seen the picture, haven't we? So if we just draw 2 to the power x itself, does it pass the horizontal line test? Does it pass the vertical line test? Does it? Does it pass it? Does it pass the horizontal line test? So let's see, I'm going to put 10. Does this curve passes the two tests, vertical test, horizontal line test? Yes, it does, right? We can do the vertical line test. You just draw vertical line arbitrarily, it should cross the curve only once. Only once, right? It crossed it only once. It crossed it only once. That shows it's a function. Horizontal line, we draw arbitrarily. We cross it no more than once. No more than once. Why this one doesn't cross? Because the range doesn't go there, right? We cross it only once. Cross it only once. Cross it only once, right? So it passes both vertical line test and horizontal line test. It's a one-to-one function. It has inverse, right? So it passes horizontal line test. It has inverse. It is 1-to-1. Thus, it has an inverse. How many? It has a unique inverse. And we're going to call it now, instead of calling it G, we're going to call it, F of inverse. We're going to find it. Okay, we're going to find it. So now let's look at the following step. The following step is a swap. Right? The following step is a swap. If we swap these in this situation, right? If we swap here, we're going to swap and this becomes X and this becomes Y. And we also understand this involves the swap of domain and range. Right? We just look at the table. Yes, the domain and range also swapped. And then we're going to solve for Y. Solve for Y from here. Solve for Y from here. Okay, of course, in this case, we have 2 to the power X. Okay, and this is to be found. How do you solve for Y here? By definition of logarithm, what is the definition of logarithm? What's the definition of logarithm? Log base B omega equals to triangle, right? If and only if is B raised to the power of triangle equals to omega, right? Remember that definition, provided that B is greater than 0, not equals to 1, right? In our case, okay, so now I'm just referring to the definition, right? How do we solve for the Y? How do we express the Y? Y is in the position of the triangle. This is the triangle. Okay, so this is the Y in our case, right? We have B it's 2. B is 2. And Y is here. You can see that from 2 to the power Y equals omega. Omega is X. So omega is X. Therefore, Y is equals to log base 2 of X. So that's how Y is solved. So the inverse of 2 to the power X is going to be log base 2 of X. Okay, so this is so on the one hand, we see the visual and we also see the algebra. Okay, and the foundation for these inverse functions to each other is from here, right? From here. Okay, we're preparing you for alpha 57. Okay, we're preparing you for alpha 57. Okay, so now, could I find the inverse for ln x? Could I find an inverse for ln x? Of course. Okay, so we're going to find inverse for ln x. Okay, and suppose we have f of x here. And of course, we'll be asking the same question again. Does ln x have inverse? Right? Is it 1-to-1? We're so familiar with ln x, right? So what is the picture of ln x? Could you guys sketch it? ln x. What's ln x? The graph, right? We've done the graph so many times, right? So this is the time to use it. That's ln x. We know it's domain and range. Right? So this is ln x. Does it pass a horizontal line test? Yes, it does. It passes both vertical line test and horizontal line test, right? It is 1-to-1, so you can make your claim. It is a 1-to-1. It is, you can just say it's 1-to-1. And it has inverse. A unique inverse. It has a unique inverse. Okay. And let's find it. How do we find it? We're going to follow the same procedure we did here. The only difference is the rules are different. So let's find it. Let's find it. So how do we find it? Okay, we start with y equals ln x. Swap x with y, right? When we swap x with y, what else is being swapped? Domain and range are being swapped. Okay, domain and range is being swapped. Well, we saw that, right? That swapping of domain and range. Okay, just remind ourselves one more time, swap the domain and range at the same time. We swap the domain and range at the same time. And then we're going to solve for y. Solve for y, what do we get? Solve for y, what do we get? Solving for y from here. We're going to use the same definition. We're going to use the same definition we quoted, right? The logarithm definition. I'm just going to, I'm not going to do the copy and paste. Just type it, okay? The definition says log base b of omega is equals to triangle if and only if that b raised to the power of triangle is equals to omega, right? Where 0 is less than b and b cannot be equals to 1. So that basic definition we learn in logarithm, right? So now in our situation, we have this guy and we want to express y. We want to express y. How do we do that? Right? E is the base. E is the base. Log base E is shorthanded ln. Y is in the place of omega. So this is omega. X is in the place of triangle. Right? So triangle is x, omega is y. And there you go. Solving for y, y is e to the power x. You see that? So the magical source of this process is the definition of exponential, the definition of a logarithm. So we found our inverse, right? So that's our function. And our inverse. The inverse of that function, which is e to the power x. Domain and range already swapped. Domain and range already swapped and summarized. Okay, and now I think you're ready. I think we are all ready for alpha 57. Are you ready? Are you ready? All right. So let's look at alpha 57. Let's look at alpha 57. In alpha 57, I have given you 6 scenarios, okay? They're all variations from our picture. So we're gonna give inverse function and graph both function on each row, okay? So for example, the first one, okay, so alpha 57, number 1, right? The function we're giving you is f of x equals to 2 to the power x minus 1. We know how to graph this function, right? You first graph 2 to the power x and you shift up by 1 unit. If we shift up by 1 unit. Domain and range will need to be adjusted. Domain and range will need to be adjusted. Okay, and then can you graph this function with me? To graph this function with me, since we're so familiar with 2 to the power x, so let's graph 2 to the power x first. Okay. Could you do that with me? So please do that along with me. Okay, so I'm going to make some adjustment to the view. Something like that. Okay, so that's 2 to the power x. How do we get 2 to the power x to 2 to the power x minus 1? How do we shift it? How do we shift it? Do we shift it left or right or up or down? How do we shift it? Or flip? How do we shift it? Up or down, left or right? How should we shift it? We should shift it down by 1 unit, right? We should shift it down by 1 unit. We should shift it down by 1 unit. Okay, so 2 to the power x minus 1. Okay. And let's make it red. Shift it down by 1 unit. Yes? Does that confirm our guess? Does it? We confirmed our guess. Okay. Shift it down by 1 unit. As a result of this shifting, domain and range need to be adjusted. Okay. For 2 to the power x, the domain is what? All real numbers. For 2 to the power x minus 1, what will be the domain? It's still all real numbers, but the range has changed because the range, everything in the range in 2 to the power x will be minus 1. Will be minus 1. So the range, and you can see the horizontal asymptote. What was the horizontal asymptote here? The horizontal asymptote here. Let me use a broken line. Big. That's the horizontal asymptote. What will be the horizontal asymptote after we shift it down by 1 unit? What happens? It shifted down by 1 unit. It's going to be shifted down by 1 unit. Shifted down by 1 unit. So what does that tell us? It tells us the domain and range. Domain stay the same, but range has changed, right? The range, it was from 0 to infinity. Now it's from -1 to infinity. You guys see that? From -1 to infinity. So now let's summarize this piece of study, right? 2 to the power x, 2 to the power x minus 1. 2 to the power x, domain, range. In terms of domain, in terms of range, domains are the same from -infinity to +infinity. Okay, they have the same domain. But -1, it costs 2 to the power x is larger than 0. It's always a positive. That's a horizontal asymptote. 2 to the power x minus 1 is going to be what? That range has shifted. And we're studying 2 to the power x minus 1. So this is the curve we're studying. Okay, so if I remove the 2 to the power x, right? So this is 2 to the power x, this is 2 to the power x minus 1. Are you guys with me? So 2 to the power x, and this is 2 to the power x minus 1. Shifted down by 1 unit. Domain stay the same, range has changed. Now, remember, we're trying to find the inverse, right? And graph both in the same picture. So we're heading there. We're heading there. Okay, so far so good. Do you follow me? Do you guys follow me? Okay. Now, with that said and done, okay, is this function 1 to 1? Is it 1 to 1? Right? We need to answer that question, because if it's not a 1 to 1, it doesn't have the inverse. Right? So this function indeed, right, is 1 to 1 because it passes both vertical line test and horizontal line test. And thus it has a unique inverse. It has only one inverse, so let's find it. Let's find it. Okay, so let's find the inverse. Okay, when we try to find the inverse, this is the point we have been preparing you for, right? We write this as y, and we're gonna swap x and y. Okay, so x and y swapped. And this swap is gonna cause what to happen? Is it gonna cause a domain and range to swap? Okay, domain and range swap. So when we swap x, y, what do we get? We get x equals to 2 to the power y minus 1. Let me make the font just a little bit larger. See that swap? 2 to the power x minus 1, the domain and range will be swapped. Okay, and now we're going to look at the inverse. Right? The inverse function, suppose this is f. Right? That's what's in our assumption. And that inverse, we don't know what it is. We don't know what it is. Okay, we don't know what it is, but we already know the domain and range. Okay, we already know its domain and range. The domain would be larger than -1, and the range would be the swapped. You guys follow me? So this function is inverse. Okay, so let me remove that. Nah, not removing it is probably better. Okay. Okay. So now we see better, right? Now we see better. This is the function we're going to find inverse with. We haven't found the inverse yet. Okay, but we know the domain and range will just be swapped. And when did that happen? When did that happen? It happens at the moment of swap. Okay, it happens at the moment of swap. Okay, so that's swap. Let's continue. Let's continue. And of course, we're going to solve for y. Solve for y. Okay, how do we solve for y from here? Right? We're going to rewrite it as 2 to the power of y equals to x minus 1. Recall the definition. Recall the definition of logarithm. Okay, log base b of omega equals to triangle if and only if b raised to the power of triangle equals to omega, right? That key definition, of course, 0 is less than b and b cannot be equals to 1. Okay, so now let's see. The base here is 2. So this is 2. 2 to the power of y, so the triangle is y. Okay, what is omega? 2 to the power of y is omega. Omega is x minus 1. Therefore, this is x minus 1. X minus 1. So what do we get? We have solved for y. I simply apply the definition. So now we get y is equals to log base 2 of x minus 1. And that's our inverse function. Okay, that's our inverse function. F inverse of x is equals to this guy. So now we can put our inverse function in place. You got it? Okay, of course we're not done. Okay, so everything is set. Graphing them in the same picture. Let's graph them in the same picture. This is a 2 to the power x minus 1. Right? This is 2 to the power x minus 1. Its inverse, log base 2 x minus 1. How do we graph log base 2 x minus 1? How is this shifting? How is this shifted? Okay, this is the, let's put this away first. Okay, let's put this away. Log base 2x minus 1. How would you graph that? From log base 2x, oh, log base 2, sorry, log base 2x. How is the shift to get log base 2x minus 1? Is it shifting up or down, left to right? Log base 2x is something we have graphed before, right? So we can take that for granted. Yes, we can take that for granted. So you're going to tell me, okay, so let me make some adjustment to the view. So how is the next picture shift? Up or down, left or right? Up or down, left or right? How is log base 2 shifted? Make your educated guess, because we're going to review the answers in a second. There's no penalty. There's no penalty. How is it shifted? Is it shifting up or shifting down, left or right? What do you think? Is it left or right, or how is it going to be shifting? I want you to write down the answer on your paper, okay? And then the answer will be reviewed to you. There's no penalty to you whatsoever. It's just to check, whether you understand the whole concept of shifting. It's going to be shifting to the right by 1 unit, okay, horizontally, okay? So let's plot log base 2 of x minus 1, okay? We make it the color green. No, not green, not green, no, not green. We use green for symmetry. We use the color purple. You see, everything is shifted to the right. The vertical asymptote we had before, okay, log base 2x has a vertical asymptote. Okay, that vertical asymptote, I'm going to use red, broken, thick, medium. That's a vertical asymptote. With this shifting to the right, and the purple one has a new horizontal asymptote. I'm sorry, vertical asymptote. Sorry about that. Vertical asymptote, okay? The vertical asymptote is also shifted to the right. Everything is shifted to the right. You guys see that? If I am to remove this log base 2x here, you will see that very clearly. You follow me? Okay. So that's the whole picture. So now we're going to bring this purple and the red together. We're going to bring the purple and red together. Bring the purple and the red together. Okay, the purple, log base 2, x minus 1. We choose that to be a purple. There. Okay, it will be nicer if I just make some adjustment. Make this 8, make this 10. Okay, and once again, the vertical asymptote for the purple. The vertical asymptote for the purple. Okay, so that's going to be 1. And I'm going to use a purple for this vertical asymptote. There. Okay. Are they still symmetrical with respect to these two? Obviously are inverse function to each other, right? They're inverse function to each other. Are they still symmetrical with respect to that green line? Are they still symmetrical with respect to that green line? Let's draw the green line. Okay, I'm going to have this set up. Okay, this is 2 to the power x minus 1, and this is log base 2 of x minus 1. Let's see if they're symmetrical with respect to that green line, which is, I'm going to make it green. Broken. Wait a second. 2 to the power x minus 1, its inverse is log base 2 x minus 1. Log base 2 x minus 1. Let's see, did I make any mistake here? Drawing. Anybody find any mistake, any flaw? Maybe there's no mistake. Maybe there's no mistake. Okay, I couldn't think of any mistake. But there's not a symmetry here. There's not a symmetry. That symmetry is supposed to exist all the time. Log base 2 to the power x minus 1. 2 to the power x minus 1, right? And its inverse, log base 2x minus 1, domain and range all satisfied. What have I done wrong? I couldn't recall there's anything I have done wrong. Do you guys have any comments? Do you guys have any comments? Feel free. I know it. I got it. I didn't make a mistake. I did make a mistake. Did you see that? I made a mistake. Okay, I made a mistake. Where is the mistake? The mistake is here. When I isolate 2 to the power y, this should be a plus 1. This should be a plus 1. This should be a plus 1. You guys see that? If this is the plus 1, it should be shifting to the left. Okay, it should be shifting to the left. So this picture should be plus 1. It'd be shifting to the left. And the line of this vertical asymptote should be over there. I apologize for that mistake. I apologize for that mistake. So this is shifted to the left. So this guy is okay. The purple one is not. Plus 1. Ha. Okay. And the purple, and that should be -1, -1. Just shifting to the left, not shifting to the right. Now it works. Did you guys see that? I apologize for my mistake, but I hope we all learn a lesson from this process. It's an algebraic mistake that caused that flaw, that caused that flawed picture. Okay, so they're still symmetrical. Of course, they always have to. They always have to, right? They always have to. And so the horizontal asymptote for the red, the vertical asymptote for the purple, and they're still symmetrical with respect to that y equals to x, that green line. Okay, so this will see better, right? Do you guys see this better? Got it? So that line is y equals to x as always. As always. Okay, I think we have time to do another example. Ooh, I'm so happy we found that mistake. We found that mistake. Are you ready to pitch in? So let's do it. Let's do it. Okay. So I'm gonna choose number 6 to work on. Okay, we're gonna work on number 6 together. We're gonna work on number 6 together. Okay. You know what? Let's do number 4 first. Let's do number 4, and then we'll do number 6. I think we may have time to do both. Okay. So clear all drawings. Ooh, cool. Okay. So let's do the number 4. Let's do number 4. Okay, the same drill. The same drill. Okay. Number 4, we're given a g. Okay, this g is log base 3 of x minus 2. Okay, so first we need to determine how the picture look like, right? And what's the domain and range, because all that swap is going to take place. Okay, all that swap is going to take place. So we're going to have a comprehensive perspective about this function. So graphically, we can graph from log base 3, right? And then we graph log base 3, x minus 2, this is going to be a shift. What kind of shift? Left or right, or up or down? Log base 3. We know that picture, we drew it, right? We plotted point by point. We plotted point by point. Okay. So let's make the picture. We're gonna have say -8, 3, 8. Okay, so that's the picture of log base 3x. Right? That's the picture. And then we need to, from here, we're graphing log base 3, x minus 2. What are we getting? What kind of shifting is this? Up or down, left or right? This is going to be a shift to the right. This is going to be a shift to the right. By how many units? By 2 units. Okay, 2 units. So let's graph that. So log base 3 of x minus 2 shifted to the right. I'm going to use red. Let's use red. Shifted to the right by 3 units. Okay, by 3 units. I'm sorry, by 2 units. By 2 units. And the vertical asymptote, right? And the vertical asymptote in log base 3x, and that's going to be 0. Right? So that's vertical asymptote. I'm going to use purple. How about that? Broken medium. Vertical asymptote. That vertical asymptote is also going to be shifted horizontally to the right. Okay, it's going to be shifted to the right. Okay, so now it's being shifted to the right by 2 units. Okay, I'm still going to use the purple, broken medium, shifted to the right. Okay, so in terms of domain and range, what is the domain for log base 3 x minus 2? The domain for this guy, of course, we know, right? Right? For log base 3x, that's going to be x is larger than 0. And how about the domain for this guy? It has to be x larger than what? 2. Range stay the same. Range stay the same. Okay, so let's find the inverse. Okay, so range, all real numbers. Negative infinity, positive infinity. Okay, so that will be the same. For the other one. No problem. Any questions so far? Any questions? Okay, so let's find the inverse. Let's find the inverse. Right? So to find the inverse, we're going to still do the swap. Right? X swapping with Y. Okay, that swap is going to give us X, and this becomes Y. And we're going to solve for Y. Solve for Y. Okay. If we solve for Y, how do we solve for Y? Well, we will use a definition. Okay, what is a definition? Logarithm and exponential functions, right? So we have the log base b of omega equals to triangle if and only if that b raised to the power of triangle equals to omega, where b is greater than 0 and not equals to 1. Okay, so let's look at our situation here. Oops. Okay, base is 3, so base is 3. Right? The number at the omega position is y minus 2. So this is a y minus 2. A triangle position, right? That's a triangle. So that's triangle. Okay. Omega is y minus 2. So from here, okay, from this form, we get to y minus 2 equals to 3 to the power x. And what does y minus 2, what does y equal to? Just adding 2 on both sides. So y equals to 3 to the power x plus 2. Okay, so we have the picture over here. And what else do we have? Do we have the picture over here? Do we know this picture? It is 3 up, it's 3 to the power x shifted up by 2 units. So what's this 3 to the power x? We have graphed 3 to the power x, right? We have graphed 3 to the power x. What am I doing here? No, this is not pasting, sorry. Graphing. 3 to the power x. I've graphed this so many times, right? So it's handy. We just use it. Okay, we just use it. And so we just use it. So what do we have here? I'm going to use a 10. Okay, it should work. 3 to the power x. So we have 3 to the power x right here. And shifting up by 2 units. Shifting up by, I hope I didn't make the same mistake as I did before. Okay, adding 2. Okay, adding 2. So this will be shifting up by 2 units. Right? Shifting up by 2 units. If we shift up by 2 units, okay, 3 to the power x plus 2, shifting up by 2 units. We're going to use purple there. Shifting up by 2 units, right? What else is being shifted? The horizontal asymptote. The horizontal asymptote. It used to be the x-axis now. And what is it now? I'm going to use the color. Yellow. I'm going to use yellow. Broken line, medium. So this was the horizontal asymptote. Now the new horizontal asymptote would be what? The new horizontal asymptote would be what? Will be 2 units higher. 2 units higher. So it's been shifted up by 2 units. So that's our purple. So now we're going to take the purple with red. We're going to bring the purple and red together. Okay, we're going to bring the purple and red together. Okay, we're going to bring the purple and red. Okay, so I'm taking the purple. Okay, taking the purple, I'm taking the red, I'm sorry, taking the red, I'm going to remove one of these. Okay, that's the red. And my purple, where's my purple? 3 to the power x plus 2. Okay, so that's my purple. Okay, that's my purple. I'm going to make some adjustment to the scale. Okay, let's see if this will do. The scale is a little bit, I just need to adjust the frame. Okay, so this much is a 4, this much is a 4, this is about right. Okay, and the horizontal asymptote for the purple, right? The horizontal asymptote for the purple also comes with it. I'm going to use the purple, broken, medium. Okay, so these are the inverse function to each other. Are they symmetrical with respect to that line? Yes, they have to. Okay, they must. Okay. There. Right? Well, we couldn't do number 6. Okay, I encourage you guys to try number 6. And we're gonna continue that on Monday. And today's topics and what we did last time, Monday and today, there will be another quiz. Okay, this quiz will be more related to inverse functions and so on and so forth for what we did. Okay. And for the remaining time, do you guys have any questions? You can dig out a lot of other information such as intercepts, right? For example, the intercepts, x-intercept, y-intercepts, right? And I could be asking you those questions. I could be asking you those questions, all right? So for example, what will be the x-intercept for this guy? Well, you can go by shifting, right? The x-intercept that was here, the function before was log base 3, and after you shift to the right by 2 units, the x-intercept will be shifted as well. So you need to be able to identify these intercepts. Y-intercept as well. If you, after we shifted up, the y-intercept has changed. So you need to identify the y-intercept. And you need to be able to identify the horizontal asymptote, vertical asymptote after the shifting, after the respective shifting. You guys follow me? So some of those details we haven't attended to, but we already have done that in other settings. And so those questions may be asked of you. And so please study this section. Very, very important section. And it's also very, very difficult section. Okay, for those of you who are heading the calculus class, you are, you need to be good at this. You need to be good at this. Okay. Any other questions? Okay. I think I'm going to let you go a few minutes earlier today. And right now it's 12:56. If you have any questions, please ask. Otherwise, send me your question, send your question my way and throughout the weekend, and I'll be happy to answer. I will see you guys on Monday. Have a great day. Have a great weekend. Okay, you have worked hard. You've earned it. Okay, but you still have another quiz to expect. I'll see you guys on Monday. Okay, thank you for coming.